Okay everyone, so this video is going to be talking about solubility curves, and so this over here is a picture of a solubility curve, and what it has on it is several lines representing various chemicals and how much is able to dissolve at a given temperature, okay, which is our definition of a solubility curve, the amount of our solute which is able to dissolve at a given temperature, because we know that temperature can affect how quickly a solute can dissolve, but it can also play a factor in how much solute will actually dissolve, which is why hot coffee can dissolve more sugar than cold coffee. Not only does it dissolve faster, but you can actually dissolve like a larger quantity. And so each of these chemicals here on our graph represent the various solutes that have been dissolved in 100 grams of water. And so solubility is our y-axis, and temperature in degrees Celsius is going to be our x-axis. Now, with this graph, what it allows us to do is to plot any particular amount at a given temperature and determine whether or not we are actually able to dissolve that amount. So, for example, let's say we're talking about potassium nitrate, or KNO3. That means we're going to be looking at this line and ignoring all of the others. And so this line represents a saturated solution. And so a saturated solution, as we see over here, is the maximum amount is dissolved at that particular temperature. So we can see that that amount changes relative to the temperature. And so what happens if you add any more, then it just kind of sits at the bottom of a test tube. So if you already have a saturated solution and you're adding more solute in, it's just going to sit at the bottom, which is why sometimes when you add sugar to coffee at a certain point, it reaches where no more will dissolve, no matter how much you stir, and it just sits at the bottom, making your cup of coffee very gross. And so that is a saturated solution. So if we have, for example, 70 grams of potassium nitrate at 60 degrees Celsius, that point would be right here, because we can see like where it is relative to 70 and to 60. And so that is where our point is. Now, and I accidentally erased my yellow highlighting. So this point we can see is under the curve. So at 60 degrees, the saturation point is somewhere in there. So maybe 102 grams, perhaps, given a guess, but we are at 70. So because it is below this saturation point, we would say that this is an unsaturated solution. So an unsaturated solution is when lower than the maximum has been dissolved. And so this means if you add more, it will dissolve, because there's room for that. And you can use this graph to actually calculate how much you need. If we have 70 grams and there is 102 for saturation, you can say that 102 minus 70 will give you the amount that you are still able to dissolve in that solution. Now, with a supersaturated solution, or let's say if instead of 70 grams at 60 degrees, what if we have 140 grams? Well, at this point, if you're trying to dissolve 140 grams, this is way above the saturation point. So what's going to happen is there are one of two things. So you could have option 1, or you can have option 2. Now, option 1 is going to be a saturated solution. And what this means is that you will have 102 grams dissolved, and you're going to have 140 minus 102, so about 38 grams of your potassium nitrate just sitting at the bottom of your beaker, and it just won't dissolve. However, option 2 is potentially making a supersaturated solution. Now, the way to make a supersaturated solution is we see that at 60 degrees, 140 grams is not able to dissolve. However, if you were to heat your solution up just a little bit to where it was at 80 degrees Celsius, well, now this is below the curve and that would all dissolve. And so what happens is if you heat it to a high temperature and then slowly cool it back down, you're able to almost like trick the solution into actually keeping that dissolved. So the definition of a supersaturated solution is when more than the maximum has been dissolved. And so the key thing though is that if you are looking at the problem and your point is above the curve, then you really have to make sure that it says, and it's all dissolved. Because if it's not, then you have a saturated solution with a lot left over in your beaker. Now, an example of a supersaturated solution is sweet tea. Okay, I am from Atlanta and I love sweet tea. It's just a thing that we do. And so if you are wanting to make sweet tea, you need to put a lot of sugar in it, but not when it's cold. You have to use extremely hot water, almost boiling water, to dissolve the amount of sugar that you need. And then when you add colder water to it and you put it in the fridge and you put ice in it, it does get colder, but your sugar still stays dissolved. And so that's kind of the idea of what this solubility curve is you're tricking the solution. Now, I'm going to put another video from a chemistry teacher who did an amazing thing with supersaturated solutions. It's a good video, I think. But the main idea is supersaturated solutions are very sensitive. If you add just a little bit to them, depending on how sensitive or how truly concentrated they are, they can completely be disrupted and all of the solute can come back out of solution as crystals. So now that we're kind of understanding this graph and really how it works, let's look at just some practice problems of like what are some things that you could be asked to do. So for example, if it says which of the salts shown on the graph is the least soluble in water at 10 degrees. So key things here, we have our temperature and they want to know least soluble. So that means it's going to have the lowest amount that's able to dissolve. So if we look at 10 degrees Celsius, we can see that the first line we reach is this point here. And so that would be KClO something. Let's see. If we zoom in, can we read it? KClO3. So potassium chlorate. So that would be our answer. So KClO3. Now, number 2 says, which of the salts shown on the graph has the greatest increase in solubility as the temperature increases from 30 degrees Celsius to 60 degrees Celsius? So this one, when it's talking about here, it says the greatest increase in solubility. This means you're looking at the slope. They're asking like which one is changing the most from 30 degrees to 60 degrees. So 30 degrees is here and 60 degrees is here. And if we look, we can see that right here, KNO3 has the sharpest curve or slope. And so we can measure that by taking the solubility at the end at 60 degrees and subtracting 30 degrees and actually getting a differential and a change. However, we can just visually tell that this one has a larger change than its next most prominent one, which would be sodium nitrate. So it's really going to be that potassium nitrate there for the win. Now, number 3 says which of the salts has its solubility affected the least by a change in temperature. So this means you're looking for the slope that's going to be the flattest because it's the least change. That means your slope line should be really flat. And if we look, salt barely changes, which means if you're trying to dissolve salt, I mean, basically the amount you can dissolve at 10 degrees is the same amount you can dissolve at 100 degrees, so it does not matter if that water is boiling. That line is very, very flat. So that's what I would go with. Now, number 4 says at 20 degrees Celsius, a supersaturated solution, okay, so it's supersaturated, contains 100 grams of solute in 100 milliliters of water. How many grams of sodium nitrate must be added to saturate the solution at 50 degrees? So we have 20 degrees and it contains 100 grams. So that means our point is right here. Now remember, we are looking at the sodium nitrate solution, which is this pink line here. And they want to know, so it's supersaturated, right, because it's above, they've all dissolved it, and they want to know how much needs to be added at 50 degrees. So if we move our point to where it is at 50 degrees, it's now unsaturated because it's below the amount that's able to dissolve. Now this is at about maybe 112, so if we're at 100, then our answer would be 112 minus 100 equals 12 grams that are able to be dissolved in order to actually create a saturated solution at 50 degrees. Now the rest of the questions you should just be able to go through on your own. They're very, very similar. The only thing that I would like to point out is here, number 12. It says, assume that a solubility curve for a gas, such as ammonia, at 1 atmosphere of pressure was plotted on the solubility curve. Reading from left to right, this curve would do what? Well, remember, when we're looking at solubility and temperature, and this was in a previous video, remember that as temperature increases, the solubility or the ability to dissolve for a solid is also going to increase. So that means all of these lines that are sloping upwards as temperature increases, the solubility of our solid is increasing. However, there are a few here on our graph, like NH3 and cesium sulfate, that are sloping downwards, and that is because they are a gas, because as your temperature goes up, the solubility of your gas decreases. Now, it's super important to understand why this happens, because, I mean, it's great to know the trend, but keep in mind, when you have a gas, okay, and let's say this is a can of soda, and you have this solution, and you have molecules of gas. Well, those molecules of gas are bouncing all around the solution. They're moving, moving, moving. But temperature changes the speed that the atoms are moving at. So if this molecule is moving slowly towards the surface and it doesn't have enough energy to break through the intermolecular forces at the surface, then what happens is it just kind of bounces back and it stays dissolved in the solution. But if you increase the temperature and you increase the speed, so now this molecule is moving very quickly towards the surface, then it's going to have enough energy to actually break through the intermolecular forces and the gas particles escape. This is why the solubility of gases decreases. And so this escape, it's almost like a game of Red Rover. If you played that game in recess in elementary school, you know, where you said, Red Rover, send so-and-so on over. And you had kids lined up, or 2 rows of kids, and one kid would run across and they had to try to break through the grip of the other line. That's kind of like what this is. If the molecules are moving quickly towards the surface, they can escape. But if they're moving slowly, then they stay dissolved. And so this is kind of what we want to know for solubility curves. So keeping in mind, we've had multiple videos now about what a solution is, how it dissolves. Now we've talked about like how much can dissolve at temperature, how to change the rate, and next we'll be talking about how to actually measure the amount that's there, and then we'll be looking forward to our last video on colligative properties.